Last time, I gave you this 3 by 3 matrix and I asked you to compute the inverse. What we did was we said that since this matrix is invertible, then we had this theorem that said that the matrix A is row equivalent to the identity matrix. And that also means that the identity matrix is row equivalent to the matrix A. So if the matrix I, the identity matrix, is row equivalent to A, then we have a sequence of elementary matrices that when we multiply these elementary matrices with A, we get the identity matrix. And all of these elementary matrices, if you multiply them together, give you your inverse. So what we did was we took A and we tried to put it in reduced row echelon form. And the reduced row echelon form is going to be the identity matrix. So here are all the elementary row operations we did to put this matrix A into reduced row echelon form. And these elementary row operations correspond to these elementary matrices. Now again, we said that if we multiply these elementary matrices in this order, then we get the inverse. And that's what we did last time. So I wrote all 5 of the elementary matrices, and I started by multiplying these two, and I got this matrix. And then I multiplied these two, and so on. And finally I ended up with this matrix here. Now the next thing you should do is double check that you got the right answer. So you want to see that if you take this inverse matrix that you found and multiply it with the original matrix, you indeed get the 3 by 3 identity matrix. And so I've done this here. Just double check this, but running through it, you can see that, for example, the first row with the first column give us -1 plus 2, which is 1. And then you'll get 0, 0, and so on. So you do get the identity matrix. Now, if you don't get the identity matrix, that tells you that you made a mistake in your elementary row operations or maybe multiplying the elementary matrices together. So you need to go back and fix your mistake. Okay, so the next thing I want to talk about is just a quicker way to find the inverse of a matrix. So here I have that same matrix, this 3 by 3 matrix. And what you're going to do is you're going to copy this matrix, and we're going to put it right here. And I'm going to erase this line, and I'm going to put a straight line here, and then I'm going to put the 3 by 3 identity matrix here. Now we already found the inverse of this matrix, so I'm just showing you another way to do it that is a little bit quicker. I'm going to do exactly what I did before. I'm going to follow the same procedure, and I'm going to show you that we're going to get the inverse on this right side. So I'm going to make this side look like the identity matrix, and then this side is going to end up looking like the inverse. So the first thing we did, if you go back and review, was we took this row, multiplied it by a -2, and added it to the third row. So -2 times row 1 plus row 3. I'm going to do that again. The only thing different here is I'm also going to multiply these entries in this row by this -2, and I'm going to add them to these entries. So let's see. I'm going to cross this out so I don't make any mistakes. So -2, -2, -4, -2, 0, 0. Add it to this one. We get 0, -1, -2, -2, 0, 1. Now what I want you to notice is that right now, this is the elementary matrix E sub 1. Let's scroll up to double check. Here I wrote all of them out. Here's E sub 1. Okay? Now let's continue this process. I'm going to do one more. If you recall, the second thing we did was we multiplied this last row by 2. So we did 2 times row 3, and then we added it to row 2. That way we can make this pivot a 1. Okay, let's do that. So I'm going to cross out this row, multiply it by 2, add it to this row, so I get 0, 1, 0, -4, 1, 2. Now look at this matrix. This matrix is E sub 2 times E sub 1. Let's look back up. So 1, 0, 0, -4, 1, 2, -2, 0, 1. If we scroll up, here I multiplied these two matrices together, and you can see this is exactly what I got when I did my second step. So if you continue this process, I'm not going to do all of this again, but continuing in the same way, what you're going to get is 1, 0, 0, 0, 1, 0, 0, 0, 1, and then -1, 0, 1, -4, 1, 2, 3, -1 half, -3 halves. The inverse. So this is going to be A inverse. And this is going to be all of those, I think there were 5 of them, 5 elementary matrices multiplied together. So each time you do a step, you're multiplying by elementary matrix. Now if you do these elementary matrices in a different order, like let's say instead of multiplying this row by a 2 and then adding it to this row, you could have flipped these 2 rows and then multiplied it by a negative. You can find other elementary matrices that multiply to give you the inverse. They won't be the exact same elementary matrices that you got before, but you'll get the same inverse when you multiply them together. Okay, so that's a quicker way to do it without having to write out every single elementary matrix. Here you're just getting the last result, the actual inverse. And yeah, if I ask you for all the elementary matrices, you should do this way that we did before, where we wrote all of them out. But if I just ask you to find the inverse, you don't have to write these out. You can just use this quicker way to find the inverse. Now I do want to mention that if you have a bigger matrix or a smaller matrix that you want to find the inverse, let's say for example, you want to find the inverse of B, where B is a 2 by 2 matrix. Let's say it's 3, 4, 1, 8. Then you're going to put 3, 4, 1, 8 here, and then 1, 0, 0, 1. You put the identity matrix that corresponds to this size. So this is a 2 by 2 matrix, so you're going to put a 2 by 2 identity matrix. If you had a 4 by 4 matrix, just make something up, and you wanted to find the inverse. Oh, I need one more line here. Remember, we only find inverses of square matrices, so 2, 2, 2, 3. Let's say you wanted to find the inverse of this, then you erase this, put a line, and put the 4 by 4 identity matrix. All right, so let's move on. I'm going to give you another example for you to find the inverse. So here I have the matrix C. It's a 3 by 3 example. You should pause the video and try to find the inverse of this matrix, and I'm going to show you the solution. Okay, so here I found the inverse. Now you don't have to use the same steps, but here is the way that I did it. So I put the matrix here and the 3 by 3 identity matrix. First thing I did was I took negative 2 times this row, and then I added to this one. And then I also added this row to the last row. So by doing those 2 steps, I get this matrix. Then I got rid of this 2. And yeah, so I did, actually, looks like I added this row to this one. And then I halved this row, and I multiplied it by a negative. Then I divided this row by 6. And then it looks like I took this row and I subtracted it from the top row. That's how I got this 2 and this 0. And then I went and took this 1 and I got rid of all of this stuff here. And so you end up with, this is your inverse. And over here I actually just put all of those fractions, I reduced them. See, I had 2 over 6, so I reduced it to 1/3. And this is what you should get for your inverse. Now you should always double check your answer. So make sure that when you multiply C with the inverse, or you could do C inverse with C, that you get the identity matrix, the 3 by 3 identity matrix. Okay, let's move on. Now here's a good question. Suppose we have A and B, they're both the same size, n by n, and they're both invertible. Is the product of 2 invertible matrices also invertible? And if it is, what is this inverse? So the answer is that the product, the inverse of a product does exist. And let's think about this. If I have A times B, what happens if I multiply it by B inverse times A inverse? Let's just consider this product. Well, this is A times the identity times A inverse. And we can multiply these 2 together. We get A times A inverse, which is the identity. So we get that A times B inverse times A inverse is equal to the identity matrix. So this is a product, and that product's inverse is right here. So that brings us to a very important fact, that A times B, its inverse is B inverse times A inverse. Okay? This is something you need to memorize. This should kind of remind you of the transpose. Remember, if we had A times B transpose, then we switched the order and put the transposes. That way it shouldn't be too hard for you to remember. And remember that this only works with multiplication. Now this does not work with addition. So A times B inverse is B inverse times A inverse. So switch the order. The last thing in this section, I know this has been a long section, the last thing I want to talk about is some special types of matrices. You're going to see these a lot in this class. So the first type is a diagonal matrix. Now this is going to be a square matrix. And so we're going to say n by n. And I'm going to give you some examples. It's going to have numbers, any real numbers on the diagonal, but 0 everywhere else. Let me make that look a little bit better. So I'm going to put the details here. Any real number including 0, on the diagonal, and zeros everywhere else. So this is a diagonal matrix. So is this matrix. I put a 0 here, but you can have a 0 on the diagonal. So the only things that are non-zero or could be non-zero are things on the diagonal. And you could also just do the 0 matrix. That is a diagonal matrix. Okay, let me ask you a question. When is a diagonal matrix invertible? So a diagonal matrix is invertible if and only if the product let's put, yeah, that's fine. The product of the diagonal entries does not equal 0. And why is that? Well, for a matrix to be invertible, remember it has to be row equivalent to the identity matrix. In order for a matrix to be row equivalent to the identity matrix, that means when you put it in reduced row echelon form, you get the identity matrix. Now, if the product of the diagonal entries is equal to 0, then at least one of the diagonal entries has to be equal to 0, right? A times, for example, A times B times C times D, if I multiply them and get 0, by properties of real numbers, at least one of them is 0. And if at least one of them is 0, then you can't have a matrix that's row equivalent to the identity matrix. Okay? What about an upper triangular matrix? So an upper triangular matrix looks like this. I'm going to put a bunch of stars here. So here's a 4 by 4 example, but you can generalize this to an n by n example. So upper triangular matrix has zeros below the diagonal. So you can have whatever you want above the diagonal, but you must have zeros below the diagonal. And here's the diagonal right here. This is the diagonal. So anything including 0 above the diagonal. I'm going to ask you the same question I asked you a minute ago about the diagonal matrices. When is an upper triangular matrix invertible? So an upper triangular matrix is invertible if and only if the product of the diagonal entries is non-zero. And this is for the same reasoning as the diagonal matrix. If an upper triangular matrix is invertible, so it's non-singular, then the reduced row echelon form of the matrix is the identity matrix, and that means all of the pivots will have to be, you'll be able to get all of those pivots to 1. And if the diagonal, if you multiply all the entries on the diagonal and you get 0, then at least one of the pivots is 0, and so there's no way that the matrix is going to be row equivalent to the identity matrix. And the last special type of matrix I want to talk about is a lower triangular matrix. And again, here's an example. I'm thinking you can guess what this is going to look like. So these stars just represent any number. And same thing with this A, B, C, and D, any number. You could put stars here if you like. So this has zeros above the diagonal. Anything else? Anything on or below the diagonal, including 0. And again, a lower triangular matrix is invertible if and only if the product of the diagonal entries is non-zero. Okay, so let me ask you a couple questions. Let's look at this matrix. Does this matrix fall into any of those 3 categories? The answer is yes. This is a lower triangular matrix. Notice that the only non-zero entries are on or below the diagonal. Everything above the diagonal is 0. So this is why they call it a lower triangular matrix, because it's triangular here and it's on the lower part. What about this matrix? What kind of matrix is this? This is actually a lower, an upper, and a diagonal matrix. That's because, well, first off, obviously it's a diagonal matrix because it has zeros everywhere except the diagonal. It's a lower triangular matrix because it has zeros above the diagonal, and it's also an upper triangular matrix because it has zeros below the diagonal. So it's all 3. Diagonal matrices are part of the lower triangular matrices and the upper triangular matrices. And then finally, let's do one more. What kind of matrix is this? This is none of those 3 options. It's not lower triangular, it's not upper triangular, and it's not a diagonal matrix because it doesn't fit into any of those categories.